A company just spent over $100 million building a data center in Virginia. The servers are installed. The cooling systems work, and it cannot turn on because there isn't enough electricity to run it. Not because America doesn't have enough power plants. It does. The problem is that the wires to connect that power to this building don't exist yet, and might not for another decade. Here's the number that explains why. In 2014, the US built 4,000 miles of new high-voltage power lines a year. Last year, less than 1,000. And by the end of this video, you'll understand why a single 230-mile power line can take longer to approve than it took to build the Hoover Dam. Let's start with why this actually affects you, even if you've never thought about a transmission line in your life. The story everyone's been hearing for the past 2 years is about artificial intelligence and how much electricity it consumes. That story is true, but the scale of it is still underappreciated. Global data center power demand is projected to hit 84 gigawatts by 2027, a 50% jump from where it stood just a few years earlier. AI workloads alone are expected to account for more than a quarter of that total. But here's the part that doesn't get enough attention. This demand isn't spread evenly across the country. It's concentrated. It's showing up in specific regions, often very fast, and utilities are struggling to keep up with the speed of that change. Between 2023 and 2024 alone, 5-year forecasts for summer peak electricity demand jumped from 38 gigawatts to 128 gigawatts, more than a threefold increase in a single planning cycle. Utilities that used to plan decades in advance with comfortable margins are now scrambling to revise numbers that are barely a year old. And it's not just data centers. Think about the broader push to bring manufacturing back to American soil. Semiconductor fabs, battery plants, steel mills supplying components for wind turbines and transformers. These facilities don't just need land, labor, and capital. They need power, often massive amounts of it, delivered to very specific locations. A new chip fab can require as much electricity as a small city. If that power can't be delivered, the factory doesn't open on schedule, no matter how much funding it received or how many ribbons were cut at the groundbreaking ceremony. This is the paradox at the heart of America's energy strategy right now. The country has seen record investment in electricity generation, solar, wind, natural gas, and a renewed push into nuclear. Generation isn't the bottleneck. The bottleneck is everything that happens after generation, the wires that move that electricity from where it's produced to where it's needed. And those wires are aging. Roughly 70% of the US grid is approaching the end of its functional life cycle. Much of it was built between the 1950s and 1970s, designed for a world where electricity demand grew slowly and predictably. That world doesn't exist anymore. The grid that's supposed to carry power to AI clusters, chip fabs, and reshored factories is in large part the same grid your grandparents' generation built. So when people talk about an energy transition, they usually picture solar panels and wind turbines. But the real transition, the one that determines whether any of that new generation actually matters, is happening in transmission. And that's where things get complicated. To understand why transmission has become the bottleneck, you need to understand the difference between two things that often get lumped together: generation and transmission. Generation is the part most people are familiar with. Power plants, solar farms, wind farms, nuclear reactors, these produce electricity. Transmission is different. It's the network of high-voltage lines that carry that electricity over long distances, often hundreds of miles, from where it's generated to the substations that eventually distribute it to homes, businesses, and factories. Building generation has gotten relatively fast. A utility-scale wind or solar project can typically go from approval to operation in about 4 years. Transmission lines are a different story entirely. On average, a new transmission line takes up to 10 years to move from initial planning to completion. In some cases, it takes considerably longer. Why the massive gap? Picture it like this. Building a power plant is like building a house. You need one piece of land, one set of permits, one set of neighbors. Building a transmission line is like building a 100-mile-long house, one that needs permission from every single property owner, county, and state government along the way, and where any one of them can say no. Start at the federal level. Before a major transmission project can even break ground, it typically needs to complete an environmental impact statement, a process that on its own takes roughly 4 years on average, from the initial notice of intent to the final decision. That's just one document, but it's one of the most consequential because it triggers reviews from multiple federal agencies. At least 9 separate federal agencies can be involved in approving a single transmission project, each with its own process, its own timeline, and its own criteria. 9 agencies for one power line. And federal approval is only the beginning. Unlike a power plant, which sits in one location, a transmission line is linear. It crosses through multiple counties, multiple states, sometimes multiple federal jurisdictions. Once federal approvals are secured, developers then need separate approval from the Public Utility Commission of every state the line passes through. They also need to acquire rights of way, either by purchasing easements from private landowners or, in some cases, pursuing eminent domain. Every one of these steps can trigger legal challenges, and those challenges can add years to a project that was already taking years. Add it all up, and since 2005, new transmission projects have taken more than 10 years on average to complete. Longer interstate lines tend to take even more time, because more states means more opportunities for delay at any single point in the process. There's no better illustration of this than the SunZia transmission line in New Mexico. SunZia is designed to carry wind energy from one of the best wind resources in the country to markets that desperately need it. The project became notorious in energy policy circles for one simple fact: it took 17 years to permit, not to build, to permit. 17 years of environmental reviews, route changes, legal challenges, and negotiations with multiple federal agencies and state governments before a single major tower could go up in many sections of the route. The line is finally expected to begin delivering electricity this year, nearly 2 decades after the process began. 17 years. Think about what that actually means. In that time, the technology for wind turbines went through multiple generations. The cost of renewable energy fell dramatically, and the demand for electricity, driven by AI, reshoring, and electrification, fundamentally transformed. SunZia is finally being plugged into a grid that looks almost nothing like the one it was originally designed for. So why does this keep happening? Why, despite broad agreement that America needs more transmission, does the system keep producing these multi-decade timelines? The uncomfortable answer is that delay isn't just an accident of bureaucracy. In many cases, delay serves someone's interests. Consider existing power generators in a region. If a new transmission line brings cheaper electricity into their market, say low-cost wind power from a neighboring state, that can lower wholesale electricity prices and reduce demand for the power those existing generators sell. Some of the companies most capable of influencing local regulatory processes have a direct financial incentive to see new transmission projects delayed or blocked entirely. Then there's the geography problem. Transmission lines are linear, which means they often cross states that receive none of the direct benefit. A line might carry wind power from Kansas to population centers in Illinois, but the communities in the middle, the ones living with new towers on or near their land, don't necessarily see lower electricity bills or new jobs. State regulators tend to weigh in-state costs and benefits more heavily than benefits to the broader regional grid. That makes it structurally difficult for long-distance lines to win approval in every state they pass through, even when the project makes sense for the grid as a whole. But here's the twist that catches most people off guard. You'd expect the biggest obstacle to clean energy infrastructure to come from fossil fuel interests, or from communities that don't want change. Often it's neither. Take Greenlink North, a planned high-voltage line in Nevada that's been stalled for close to a year over siting disputes. The legal challenges holding it up weren't filed by an oil company. They were filed by environmental groups, arguing that the specific route chosen for this clean energy transmission line would damage sensitive landscapes. Sit with that for a second. A project built to support the clean energy transition, delayed by the same kind of organizations that fight for the clean energy transition. It's not a story of villains and heroes. It's a collision between two priorities, building fast and building carefully. That the current process simply isn't designed to resolve quickly, and it's not just lawsuits that can freeze a project. Sometimes all it takes is a change in Washington. The Grain Belt Express, an $11 billion transmission project designed to move wind power across the central United States, found that out the hard way. In 2025, the Department of Energy terminated its conditional loan guarantee commitment for the project, which forced a pause in its federal permitting timeline. For months, the project sat in limbo, not killed outright, but not moving forward either. It wasn't until early 2026 that the project sponsor requested to move it back into active federal review. An $11 billion project paused for months, not because of engineering or even local opposition, but because federal priorities shifted. Put these pieces together, and you get a system where federal agencies, state regulators, existing market participants, local communities, and environmental groups all have legitimate roles to play, but no mechanism that forces those roles to resolve quickly. Everyone has a seat at the table. Almost no one has a deadline that actually sticks. Remember that data center in Virginia from the start of this video. Its empty servers aren't just a local problem. They're a symptom of something much bigger, a geopolitical one. The current administration has made winning the global race in artificial intelligence a top strategic priority, and energy affordability has become one of the few genuinely bipartisan issues in Washington. Both of those priorities run directly into the transmission bottleneck. If American companies can't get enough reliable, affordable power to their data centers and AI training facilities, that capacity gets built somewhere else, in countries where governments can move faster, even if that speed comes from more centralized decision-making and fewer layers of regulatory review. This is where the United States faces a structural disadvantage that has nothing to do with technology or capital. Countries with more centralized infrastructure planning, fewer competing layers of state and local authority, fewer avenues for legal challenge, can often move transmission and industrial energy projects from approval to operation in a fraction of the time it takes in the US. That's not necessarily a better system overall, but in a head-to-head race for AI infrastructure and industrial capacity, speed matters. And right now, it's an area where the American system is structurally slower. Here's the part that should really get your attention. The supply chain dimension makes this even more concrete. Every reshored semiconductor fab, every new battery plant, every steel facility supplying components for transformers and wind turbines, all of it depends on getting electricity to a specific site on a specific timeline. You can subsidize a factory, you can fast-track its construction, but if the transmission infrastructure to power it is stuck in a permitting queue, the factory's opening date slips and slips and slips again. The entire reshoring strategy, fundamentally about reducing dependence on foreign supply chains for critical technology, runs through transmission lines that, on average, take a decade to build. This is exactly why 2026 has become a pivotal year for transmission policy in Washington. In March, the Energy Bills Relief Act was introduced, which would grant the Federal Energy Regulatory Commission direct siting authority over certain interstate and interregional transmission lines, effectively giving a federal agency more power to override state-level gridlock. The following month, the Grid Expansion and Reliability Act was introduced, which would transfer the authority to designate priority transmission corridors to FERC and allow self-certification for new facilities built within those corridors, cutting out additional layers of review. Both bills represent a significant shift in the balance of power between federal and state authority over energy infrastructure, and both are moving through Congress with an unusual sense of urgency, driven in part by the approaching 2026 midterm elections. There's a recognition on both sides of the political aisle that if permitting reform doesn't happen before the midterms shift the political landscape, the window for this kind of structural change could close for years. But before you assume this is unfixable, consider this. The Department of Energy's CTAP program, the Coordinated Interagency Transmission Authorizations and Permits Program, is designed to consolidate federal environmental reviews and permitting under a single coordinating agency, with a binding 2-year timeline instead of the historical average of 4 years or more. If implemented effectively, this alone could meaningfully compress the federal portion of the approval process. There's also regional progress worth noting. MISO, the regional grid operator covering much of the Midwest, has approved a $3 billion plan for 18 new transmission projects, with an expected completion timeline of 7 to 9 years, down from the historical 10 to 12. That's still a long time by most standards, but it represents a real, measurable improvement. Perhaps the most underappreciated solution doesn't involve building new transmission corridors at all. It's called reconductoring, replacing the conductors on existing transmission towers with advanced, higher-capacity cables. Because the most contentious part of any transmission project is almost always the corridor itself. The new land, the new towers, the new environmental review, reconductoring sidesteps most of that entirely. Research from the Energy Institute at Haas at UC Berkeley found that advanced reconductoring could significantly expand U.S. transmission capacity at a fraction of the cost and time of building new lines. precisely because it avoids the siting fight altogether. There's also a historical example that suggests this problem is solvable with the right approach. In the 1990s, Texas developed its competitive Renewable Energy Zone program, an effort that engaged the public early in the planning process, in exchange for significantly shortened permitting and review timelines later. It wasn't perfect, but it demonstrated that early structured public engagement can meaningfully compress the back-end legal and regulatory fights that typically drag transmission projects out for years. At the same time, it's important not to oversimplify this as a problem with an easy fix. Permitting reform isn't politically neutral. It touches on fundamental questions about the balance of power between federal and state governments, and about how much weight environmental review should carry relative to development speed. Reasonable people disagree, often sharply, on where those lines should be drawn, and that disagreement is exactly why permitting reform has stalled in Congress multiple times before, even when there's broad agreement that the status quo isn't working. So where does this leave that data center in Virginia? Right now, it's a $100 million building full of servers that can't run. Whether it's still sitting empty 3 years from now depends almost entirely on what happens with the things we just talked about. Whether CTAP's 2-year timeline actually holds, whether reconductoring gets deployed at scale, whether Congress passes permitting reform before the 2026 midterms reshuffle the political deck. This isn't a story about America lacking the technology to build a modern grid, or the capital, or even, in the broadest sense, the political will. It's a story about how America's own governing structure, the careful, deliberate balance of federal authority, state sovereignty, environmental protection, and local input, is colliding with a 21st-century economy that doesn't move at that pace. AI infrastructure, reshored manufacturing, and energy security all require speed. The systems built to review and approve the infrastructure that supports them were designed for a different era, one where electricity demand grew slowly, predictably, and without urgency. So picture that data center again.